Thank you very much. Thank you. Thanks for the introduction again, and thanks to the organizing committee as well for this opportunity to present today. So my name is Feras Alkhalil. I'm Director of R&D in PragmatIC, and today, sort of after 2 days of quite exciting and interesting kind of talks around applications, flexible electronics, and where we see this going forward, I'd like to share with you our vision at PragmatIC of where we see ubiquitous electronic applications, and specifically here, ubiquitous sensor electronics. So to start with, just to give you an introduction about PragmatIC, we just passed our 10th years anniversary, actually, end of last year, and we are 100 plus staff split across 2 sites. The main site headquarters is in Cambridge, and we have our production R&D facility based in the northeast of England in Sedgefield. We have over the past 5 years or so, we have a number of key partners that help us through our journey, and those are also our investors. So the key investors at PragmatIC are ARM, very well known, and they're kind of #1 in the IP semiconductor industry. And we also have Avery Dennison, who's one of our key partners, Fortune 500 company, is the market leader in RFID tags. And we also have Cambridge Innovation Capital, who's supported PragmatIC from the early start as well. So I'd like to start by sort of raising the question of why ubiquitous electronics, why ubiquitous sensor electronics, or actually why even the need for kind of additional sensor activity. So there's been a lot of very nice talks over the past few days. Very nice plenary talk earlier today about healthcare applications, as well as even within this session. And there's clear benefit in terms of helping human health, improving that, and sort of clear benefit in terms of where we see these for good health and well-being applications. But the reality is, for across the world, for actually something to have impact, not only in developed countries, but also in low-income countries, as well as actually within even developed nations, disparity between poor and rich communities is significant. So some of kind of examples of this, there's currently a 90-year gap in life expectancy, not only between rich and poor nations, but actually even within rich nations as well. So it's a quite a big issue, and it comes down really to healthcare inequality. So there are solutions, there are technology advancement, there are products even in the market that are able to address a number of the issues in terms of health and well-being, but they come at a significant cost, either in terms of actual introduction cost or even environmental impact associated with that. So for really this to take hold, it has this kind of ubiquitous aspect of it in terms of cost of introduction, as well as sustainability of these solutions as well. So another example of this kind of area is sustainable food requirements, where a lot of the food we produce globally, we end up wasting. So around a third of all food produced ends up getting wasted annually. We also have large environmental footprint associated with this food waste. So that corresponds to a third of the third largest emitter of CO2 emissions. So it has significant impact, not only in terms of increasing the disparity between rich and poor communities, but also it has a clear impact on the environment and climate and so on. Another example is, of course, very well known in terms of plastic waste and plastic packaging. So we are really at kind of dismal rates in terms of when it comes to actually using kind of plastic packaging and resources in that sense. So only 14% of plastic globally is actually reaching recycling plants, and even then, only 9% of those are then to recycling and reintroduction into supply chains. In the UK, for example, we're dealing with sort of 60 million on average plastic bottles every day that are failing to be recycled. So again, this has large impact not only in terms of cost and the products themselves and sort of conventional commercial requirements, but also in terms of the climate, but also the local and global environments, land and water and so on. So this is kind of where it goes back to any solutions around sensor applications or electronics or emerging electronics. They need to come in with a view of sort of the global requirements, actually towards making impact and making them things that translates the improvement in everyday life for everyone around the world. So a lot of you, I'm sure, are familiar with the Sustainable Development Goals that the UN announced in 2015. Those are kind of 17 really targets are meant as a blueprint for the whole world to act towards 2030 to achieve these requirements. Of course, we're kind of doing better, slightly better compared to others on those, but we're still significantly far away from delivering that. So the technology advancement, the material, the processes that we've been hearing about over the past 2 days have been great and allowed really great improvements. Continuous monitoring has gone a long way. However, all of those, most of them are actually utilizing silicon technology, silicon electronics. And that in itself is an issue in terms of cost and sustainability. So we at Pragmatic really think that towards addressing a lot of these challenges, you need to start with actually the ubiquitous aspect of it, decentralized, democratized solutions that enables these solutions to really take hold. So cost and sustainability of the underlying technology goes a long way towards addressing that. So of course, the disparity in human health, the availability of improvements in recycling, food waste reduction as well, all of that can clearly have benefits to everyone. So solutions like monitoring human health, point of care diagnostic, as well as continuous monitoring, have a strong impact, enabling those to be accessible using kind of low-cost technologies, but also with low environmental impact. Our key ability to improve recycling rates, for example, plastic packaging, things like the example I mentioned about the UK consumption of plastic bottles, initiatives like reverse vending machines can go a long way to addressing that. All the way to actually solutions that not only kind of into the high value and high cost applications, but even thinking about animal and plant welfare and so on and so forth. So a lot of people around the world rely on kind of limited availability of stock or livestock or even kind of farming communities, which basically solutions there that can translate to something that is a fraction of the cost of the current technology can have a huge impact in addressing these challenges. So this is where we think of the underlying technology, and this is where kind of our aspiration, our technology comes in to play. Pragmatic is a flexible integrated circuit manufacturer. We make what we call Flex ICs, and Flex ICs are a fraction of the cost of silicon solution. So we believe that the underlying technology, what it offers in terms of cost and environmental impact, can provide power, communication, processing capabilities for the ubiquitous sensing applications. So Flex ICs themselves are subsense electronic circuits. They're environmentally friendly in terms of the material included, as well as the manufacturing and production processes. They're by default inherently tens of microns thick, so they have this conformal and flexible aspect that allows them to be introduced in a lot of applications, from smart packaging all the way to sort of tag applications, so on and so forth. So they have inherent capability in terms of form factor that supports numerous applications. So our Flex IC are currently kind of, we have three business model aspects that we focus on. One is our RFID tag product, so that's this connected product. So we have low cost integrated circuits, flexible integrated circuits for RFID application that enable the Internet of Things applications. We have also a Flex IC foundry that supports rapid iterations of new design using our technology. And we also have our Flex Logic, which is our revolutionary semiconductor manufacturing platform that enables distributed manufacturing worldwide for the Flex ICs. So I'll give you an introduction into each of these solutions, each of our offerings. So in terms of Flex ICs for RFID applications of the Connected family, RFID in silicon have existed for quite a while now, and they're well known as an application here. However, they're exclusive to high value applications. Sorry, so it's a certain cost point that allows silicon RFID tags to come in, and in that sense, the value of the application is then limited to the final cost of the product, which makes it quite limiting. What we provide here with our Connectic RFID tags is a 50% lower IC cost and over an 80% inlay cost reduction, which means, as well as an ease of construction, which means these RFID tags can be integrated to a lot of low cost items, a lot of consumable, fast-moving consumer goods, all the way to soft drinks, water bottles, and so on. But beyond the commercial benefit of only fast-moving consumer goods, but also you can see the benefits here in terms of tracking clinical samples, vaccines, authenticity of such items, so on and so forth. So it's quite an enabler in terms of a lot of applications that allow waste management, waste reduction, so on and so forth. The other aspects is related to the Foundry, FlexIC Foundry. So what we mean with the FlexIC Foundry, it's quite a novel approach that we've developed here, where we share our process design kit that includes our devices, the models of the devices, and the design rules associated with them, as well as the cell library for designing larger circuits and configurations. We share them with our customers. In addition to that route, we also have the conventional route, which is a lot of the semiconductor industry is familiar with, which using standard electronic design formats, cadence, Mentor, synopsis, and so on. So designers can share with them their designs and circuitry in their native formats, and that feeds into our Foundry model. And what happens there is once a product is specified using those design elements and input files, and it goes through cycles of tape out, design, layout, initial fabrication, test and verification, and so on. So these cycles can be repeated as much as needed with the customer, and of course, data and samples are shared with the native format of flexible IC in terms of thin form factor, in terms of all the benefits associated with the technology. So what FlexIC provides in terms of this Foundry model is really translating the cost benefit and the benefits associated with technology directly to customers who are used to dealing with conventional semiconductor, conventional electronics, and so on and so forth. So the whole design cycle, the whole Foundry production, from design to production to delivery to customers, actually within weeks, and we're dealing with a 90% lower cost in price wafer compared to conventional method, as well as an 80% lower upfront cost. So turnaround time is 10 times, if not more, faster than conventional electronics. So that allows people to really take their concepts from design to prototype to scale in a matter of weeks and months compared to months and years and so on. So that's the second really key enabler to ubiquitous electronics, ubiquitous sensing applications. The final aspect of current offerings we have is our manufacturing capability itself. So FlexLogic is a fab in a box concept where we have a number of processing modules connected to a racetrack system with the substrate transferring between the different stations, getting the different processes that they require. So the system is a compact footprint with complete control through proprietary automation software. So hardware and software running the line. So the line is actually requires much more significant, so it runs at a much faster cycle times compared to conventional manufacturing lines. It also operates with a much lower, smaller number of operators and oversight. So much more efficient way in terms of manufacturing that translates to the turnaround time and the cost, but also has significantly lower production costs and environmental footprint, energy usage, and so on and so forth. So all in all, it is really one of the cornerstones to enabling the sort of ubiquitous applications, because they need to be sustainable, they need to be low cost, they need to be scalable as well. And this platform enables that. The Flex Logic platform is also based on a distributed manufacturing approach. So we really see this this manufacturing platform is where you can see it produces different applications, different places around the globe, and can be scaled easily and with technology transfers improved as needed. Beyond the current technology offerings we also have some advanced technology capabilities that are currently in the pipeline. One of the ones I'd like to share with you today is our scalable Schottky technology. So this is high frequency operation technology based on our existing manufacturing processes and material sets. So it's a process that runs on the Flex Logic line that I showed you earlier in the earlier slide, and it runs without any expensive metal materials, but using exactly same material sets. So this allows high frequency operations, it allows energy harvesting, it allows passive system to operate. And the current implementation we have has already been demonstrated to operate above 2 gigahertz with an added benefit of kind of tailoring the performance metrics by the design. So the example here shows you that by controlling the dimensions of the device, you can actually tune the right characteristics there as well. Another example of an advanced additional technology capability we have added here is our non-volatile memory. So we have also implemented or demonstrated using our current process and our current materials and techniques. We've demonstrated a non-volatile phase change memory application. So this allows basically at this stage we demonstrated write once capability, and we're currently working on rewritable application. So if you can imagine sort of passive smart systems, capability like this allows the system to store certain metrics onto the smart system till it's powered again and enable to update that on demand. So it's really one of the cornerstones as well to enabling these smart systems and platform offerings. To kind of go back to the theme I've started with earlier about healthcare, and obviously it's one of the important topics that we all kind of care about and think about in terms of the immediate application, how these impact real life. So kind of a couple of examples of case studies that we're working on and how we see our technology kind of really creating impact in this area. So one of them is a project with the NHS and a company called SamplePod. So this is around pathology samples tracking, and it's really around utilizing the RFID tag as a kind of universal solution to help make impact on real world problems, current problems that currently are being dealt with. So the NHS, for example, runs through a large number of clinical samples through their processing centers using nothing but sort of conventional paper-based or computer-based or whatever it is, kind of conventional manually filled tracking for their clinical samples. So without need to expand on this, I'm sure you can imagine the complications and inefficiencies associated with that. So the project here is basically takes RFID tags that are low cost, that are conformable, and applies it to oddly shaped, irregular sample pods, because that's the conventional samples that are used. And then that applies directly to that. And this is going through kind of stages of development and validation with SamplePod and NHS. But it's a clear example of where, a technology solution at low cost, with the sustainability aspect included, can have a huge impact and benefit to existing supply chains, and in this case, pathology samples. Another example is around the capability of the technology to provide processing and computing for smart system. And in this case, the example is really on sensing with the innoLAE platform. So the demonstration you see here is the state of the art really in metal oxide circuit complexity. So we have 3,000 plus active devices in less than a 5.6 millimeter platform with a custom machine learning engine developed by ARM. So this showcases that you can actually get to a level of computing and processing with low cost technologies. And of course, there's going to be limitations where you'll never be able to reach the capabilities the silicon provide. However, these will take us a long way in terms of achieving a lot of the goals we demonstrated, point of care analysis, point of care processing, edge processing, so on and so forth, can and will be enabled by this kind of technology. I'd like to wrap up really with just kind of revisiting the vision of where we see flexible electronics and pragmatic flexible IC technology. So our aim is to improve everyday life, and the mission is to achieve that by supporting innovation from everyone, leveraging and utilizing our technology. So applications such as healthcare, such as waste reduction, food waste reduction as well, can all be enabled by solutions, combining really existing solutions, but also coming up with brand new innovations using the unique technology platform that we offer. And of course, so again, over the past 2 days, we saw numerous applications of where that's possible and innovations. This is almost dated in comparison to that, but examples of where state-of-the-art work has been happening, flexible electronics for healthcare, from Eindhoven, for example, on the left, where flexible platforms are being used for ECG monitoring, kind of low cost, low environmental impact, but conformal form factor, all the way to more kind of advanced ways of not only detecting and highlighting issues in terms of monitoring, but also offering opportunities to oxygenate and help healing process. So all those kind of things actually combined with the right technology platform and supported by low-cost flexible integrated circuits could actually have a huge and real impact on everyday life. So I'd like to end my presentation with our vision of healthcare, and in this case, sort of healthcare 4.0 as we see it. So with the right ubiquitous, low-cost, sustainable electronics platform, you can see sort of applications utilizing kind of track applications where, patient monitor, you can do patient information, documentation, as well as tracking samples and pathology samples, all the way to surgical kits through operations, all done within the same platform. And these solutions are actually being explored and implemented globally. One example is Danish hospitals are looking to implement this kind of type of technology with RFID across all of their health providers, all the way to the more advanced way of actually verifying the authenticity and sort of quote unquote freshness, but also the use cases for use by dates and so on for vaccines, drugs, and so on, making sure that these are within their operational times and range.
If I may
yes.
interrupt you, because we're running out of time, to leave some time
of
for
course.
question.
Yes,
I think you finished more or less. So thank you so much.
Yes, thank you very much.
Thank you so much for this very insightful presentation. I have one question from Emre. Thanks for the good talk. In your opinion, what is more important in the domain of sustainable flexible electronics, recyclability of electronics or biodegradability, composability of them?
That's a very good question. I think the answer is really hard, but the reality is likely both aspects, because we're going to have to deal with short-term application as well as long-term applications. So certainly in some cases, you need to care about the recyclability in short term. And for example, that applies to all the waste that we're currently dealing with, plastic waste and so on. So in that sense, we need to apply that to existing recycling streams and enable them to go further. And in that case, the recyclability aspect and how not only the plastic product itself, but also the IC, that can go through the same recycling scheme and doesn't require separate electronic waste itself. If we think about healthcare applications and plant and food waste and all of those, then of course we need to think about bio compatibility and biorecyclability. So those are then become more relevant. So I think both aspects are very important, and we need to certainly make improvements and developments in both areas.
Thank you, Feras. And very briefly, if you could reply to the next question, how easily can you integrate MEMS sensors that exist on consumer devices, such as IMUs or GPSs, onto your circuits? Sure.
So it really depends on the complexity and what kind of aspects you're looking for. So easier, the answer is simply easier to integrate some than others. So there's a lot of demonstrations, and certainly in our experience as well, there's a lot of cases where we bring this necessary element and we can actually integrate it into the stack, either at the top or the bottom of the stacks, and in that case, provide a solution that's integrated. And in some cases, either because of performance limitations or compatibility and so on and so forth, you may end up with having to have them kind of a discrete elements in a sense. But even on the discrete element level, you're still having quite a benefit and advantage to existing solutions in terms of cost and in terms of form factor and sustainability and so on and so forth.
Thank you very much, Feras. It was very
Thank you very much.
nice
Thank
talk.
You.